So let's begin. So hello everyone. I hope you can hear me. I'm Mr. Shishidhat. I am a PhD student associated with the Systems and Control Group in IIT Bombay. I'm also the DA for this course, EE90. So this is the fifth week's tutorial session. So let's begin. Alright, so let's begin by recalling what was done in this week. So I'm going to write down the main topics. The first one was organization of the state space system. So and after that there was discussion about the state transition matrix. Or the matrix explanation. So the state transition matrix plays a very important role in the solution of the state space system x dot equals ax plus bu. Or one of the simpler systems is the homogeneous system x dot equals ax. So first we have the solution of homogeneous state space system. So it's the homogeneous system x dot equals ax. And then finally we have solution of non-homogeneous system, which is the most general case x dot equals ax plus b. Alright, so let's begin with the first one. Okay, so you have some matrices A, B, C, and D. So for example, for x dot equals ax plus bu, let's say we are in R2. So this is going to be a 2 by 2 matrix. And what the objective is to convert this A matrix into some new A matrix. Let's call it the diagonal matrix AD, such that the only non-zero elements are on the main diagonal and we have zeros on the rest. So if we can recall from the lecture that this is actually equal to lambda 1, lambda 2, zeros for the simple second order case. Alright. So we have some states x here for this model, and when we change the matrix A, we have some states y here. So we need to find the relationship between x and y. So for example, the new state y is some transformation p which acts on x. So if this is the case, then so this implies that x is actually p inverse y. So one of the main conditions for p is that p has to be invertible so that we can go back and forth between the two states x and y. So p must be invertible. So we already have the state space equation for x. So let's substitute x there. So we have p inverse y. So d by dt. This is p inverse y dot. This is a p inverse y. So here we are assuming that p inverse is time independent. Plus some b times a. So we want to get to the state space equation for the states phi. So let's just pre-multiply by p on both sides, and we have PA, P inverse y plus PB. So this is the system, new system, when this is the transformation. However, just note that if the transformation that we are defining is something like this, then this is the old state, this is the new state, then these matrices would be different. So whenever you are given a new modified equation, just make sure what is the transformation. Alright, so this is here. Let's look at the question. Okay, so we have a third order system, so I'm going to write down the matrix A directly. So it's -4, 1, 0, 0, -3, 1, 0, 0, and -2. So we have to find what P is so that we can find the transformation to the new state. Alright. So to find P, we need to find the eigenvalues lambda and their associated eigenvectors Vr. Alright. So we first need to find out the eigenvalues. So let's see A minus lambda I. So -3 minus lambda and -2 minus lambda, and the rest of the entries remain as they are. So the determinant is simply so then what are the eigenvalues? It is -2, -3, and -4. Okay, so these are distinct eigenvalues. So we have unique associated eigenvectors. So let's run those out. So it is -4 plus -4 plus 2, and then -3 plus 2, and 0. And then we have the eigenvector b. So let's say lambda 1 b1 equals b1 b1. Alright, so we just have two equations because this last row is just 0. So let's see, -2 v1 plus v2 equals 0, which implies that v2 is 2. And when we have -v2 plus v3 equals 0, this implies v2 equals v3. Okay, so let's say that v1 is 1. So the associated eigenvector becomes 1, 2, and 2 transpose. Okay, so we have to find those other two eigenvectors similarly. So for lambda equals -3, we have a minus lambda b equals since the non-off-diagonal elements will be the same, so single 1, single something. So first one is -4 plus 3, then 0, and 1. Alright, so the first equation is -u plus v2 equals 0. So v1 and v2 are same, and these two rows are the same, so we just get that P3 is 0. So the associated eigenvector is 1, 1, 0 transpose. Alright, now the eigenvector for the last eigenvalue, yeah, -4. So let's see. Again, the off-random elements. Let's complete the main values. This is 0, this is 1, and this is 2. So the first equation is simply V2 equals 0. Second equation is V2 plus V3 is 0. Okay, so this implies that V3 is 0. And the last equation is 2V3 equals 0, which is the same as this one. So what's the eigenvector then? It's any constant. We can take it to be 1, 0, 0, transpose. Okay, so recall how the transformation matrix P is calculated. So uh, let's say for lambda equals -2, -3, -4. I'm saying that the first eigenvector is, for example, V1 here. This is R3 now. Then we have V2 and we have V3. You can use some other symbols if you get confused by this vector. That's totally fine. So the transformation matrix becomes P. So you just have to arrange the eigenvectors column wise. So it's going to be V1, V2, and V3. Okay, so let's write this down. V1 is 1, 2, 2. The second eigenvector is 1, 1, 0. And the last one is 1, 0, 0. So just check if P is invertible. That will give you a check that you have calculated this P matrix correctly. So let's see. Determinant of P is -0, -1, let's say 0, and -1. Alright, so P is invertible. And we need to find the A matrix for the new system. So what we need to find is, let's go back for a minute, PA. Or so I think this is what it is. Y equals Px. So for x equals Py, I think it's going to be P inverse A. So this is for x equals P. So let's say this is the new A matrix. So let's denote this by A. Okay, so this is a P by 3 matrix. Let's continue the inverse. We already have the determinant. So now we need the cofactorant of this. So we have the adjoint first. Adjoint of P. First one is 0, then we have 0 again, and then we have -2. Then for 2 we have so what's the distance in there? It's 0, and then for this we have -2. And for this element, we'll join this, still -2. So this is positive. And then we have again for this is simple -1. Sorry, so we have to multiply by the values 2, so -2. This is -2. This is and then we have -2 again, and then the last one is -1. Just a second, I should check it again. Alright, so then what's the two-factor matrix? We just need to compute the transpose, right? So it's 0, 0, -2. Then we have 0, -2, 1, 2. Then we have -1, -2, and -1. So you can check this too. And then P inverse is simply, so it's going to be 1 by -2. So you can substitute that here and get 8 So I'm just going to write down the answer. So I think you already know what the answer is, right? We are trying to diagonalize the system. So the diagonal system is going to look like, so the first eigenvector was for -2, -3, and -2, and then zeros everywhere else. Alright. So now we have the next question. This is a second order system. So this is a double integrator, which is defined by, so d squared theta by dt square equals ut. So what we can imagine is that there is some pendulum. This is the angle theta. So u is the torque applied to the pendulum, and this is the differential equation for the pendulum. So this is second order. And so the first one is that we have to formulate the state space model. So that's pretty easy. second order system. So we have two states, x1 and x2. Let's say x1 is theta and x2 is x1 dot, which is theta. The matrix system. So we have to write it in terms of the matrices A and B. Alright. So x2 dot is simply u50. So we have 1 here and 0, 0. And x1 dot is x2. So we can write, let's say, so it's 0 here. X1 dot is x2. This is correct. And x2 dot is u, which implies that theta double dot is u. So we have one more. Okay. So right now we have A as 0, 1, 0, 0 and B is 0. Now it's the second part of this question. So we're defining the similarity transformation P. So the old state x is related to the new state x bar like this. So old states and new states. And I've already given what P is. So it's 1, 0, 1, 1. Okay, so now we have to find the matrices A theta and B theta. Okay, so let's first figure out what these are going to be. We have x dot equals ax plus bu. This implies we have ex bar dot. So let's say that just following the notation, these are a bar and b bar for the state x bar. Alright, so we have ax bar plus simply this we have to substitute for x. This is going to be px bar plus b. Now we are just going to p multiply by p inverse and we get p inverse ap x bar plus p inverse bu. This is a bar x bar plus b bar u. Alright, so to determine a bar and b bar, you need p inverse. And this is a second order system, so p inverse is going to be really easy. We have determinant is just 1. So we interchange these and reverse the sign of dot diagonals. So this is simply 1, 0, minus 1 and 1. Okay, so A bar is therefore P inverse AP. A is 0, 1, 0, 0. And 1, 0, 1. Alright, so 0 है 1, 0 again minus 1 times 1, 0, 1. So what do we have then? This is still 1, 1, minus 1 and minus 1. Now we have the new B matrix, B inverse B. And this is 0, minus 1. So now you have the new state space system in terms of the variable x bar. So you can observe here that this is not diagonal, right? Why? Because we have not considered the eigenvalues of A. We have not computed those and then find the P matrix using pure eigenvectors. In this question, the P matrix was already given to us and we just have to find the new modified set specification. So we have a part C to this question. Show that the eigenvalues of the system matrices of the two state space models equations are equal. So in this case, when P is not written using the eigenvectors of the eigenvalues, however, the eigenvalues are the same, then P is called the similarity transformation. So this kind of transformation preserves the eigenvalue of the system and consequently the true nature of the system. So let's compute the eigenvalues of A and A bar quickly. So we have A and A bar. So what A bar is 1 minus 7 minus 1 and A was 0 1 2 0. Alright. So we have A minus lambda I and the offline elements remain the same. Determinant is x into lambda square. Okay. So this equals 0 imply that the eigenvalues are 0 and 0. And let's see these 1 minus lambda minus 1 minus lambda. And here. Let's see. We have plus lambda square minus 1 equals 0. And this is fine, but now we have lambda square minus 2. Okay, so I think there's a mistake somewhere. Okay, so this is minus 1. Okay, so similarity transformation P preserves the eigenvalues of the original system and the modified system. Okay. So right now we will be considering a general matrix A, but we have already seen that A can be written in various forms, right? Controllable canonical, observable canonical, or the Jordan-Norman form. So if we have the A matrix in controllable canonical form, then we have a concept of the van der Waals matrix. Let me just write that down. Alright. So let me write a general A matrix in the controllable canonical form. So in controllable canonical form, we have the chain of integrators, right? So the first state derivative is equal to the second state and zeros throughout. The second state derivative is equal to the third state, zeros throughout. And then the second last state is the derivative of the last state. And then we have simply the negative of the coefficient. So minus alpha n minus 1 this is in the CCF form. So if this is the case and if lambda 1, lambda 2, till lambda n are distinct eigenvalues of A. Then the P matrix, the transformation matrix, is quite simple. So you don't have to calculate the eigenvectors and then arrange them column wise. There is a simple formula for this. So first is the row of ones. Then you have lambda 1, lambda 2 up to lambda n. Then squares of these. Okay. Okay, so then we have lambda 1 n minus 1, lambda 2 n minus 1 till lambda n n minus 1. So again this is square matrix n by n, and this is going to be invertible. So if you are given a matrix A in the controllable canonical form and you need to diagonalize the system, so you already have the Van der Waals matrix P, and this will transform A. So P transforms A into the Jordan canonical form. And what's the Jordan canonical form when lambdas are distinct? So it's basically lambda 1, lambda 2, all the lambda n's arranged on the diagonal, and then zeros everywhere else. Okay, so let's see a question on this one. So we have a third order system. Okay, so we have 0, 0, 2, 0, 1, 0, 0, 0, 1, minus 6, minus 11, and minus 6. And then we have the output 1. Okay, so you can observe that this is in the controllable canonical form, right? So this A matrix is from the controllable canonical form. The output is the first state, and we have zeros throughout, and then the non-zero quantity at the end. Okay, so the question is, characterize the system using a similarity transformation. And find the modified or the diagonalized system. So for this we just have to compute the eigenvalues and then we can arrange them like this, right? Alright, so let's compute. So it's minus lambda, minus lambda, minus 6, minus lambda, and then the octactive elements remain the same. So what's the determinant? Let's see. Okay, so it's going to be 6 lambda plus lambda square plus 11, and then minus 1 hence plus 6. So let me know if any of the computations are incorrect. So this becomes minus 6 lambda square minus lambda 2 minus 11 lambda minus 6. So we have this characteristic equation then. Lambda cube plus 6 lambda square plus 11 lambda plus 6 equals 0. Okay. So let's find out. For lambda equals minus 1, we have minus 1 plus 6 N plus N. Yeah. So one of them is lambda plus 1. Let's show the rest of them out. Alright, so we have lambda square S5 lambda plus 1 and lambda square plus 5 lambda plus 6 and the rules of this are we have -3 and -2. Lambda plus 1, lambda plus 2, lambda plus 3 equals 0. We have the lambda thus. Alright, so now let's quickly form the field matrix. So the random matrix is, it's going to be 3 by 3. It's going to be the same size as the A matrix. Then we have row 1s, then lambda 1, lambda 2 and lambda 3. Alright, and then we have 1, 4 and 9. So you can check if P inverse AP or maybe PAP inverse is the diagonal matrix or not. So what we want to get is -1, -2, -3 and series everywhere else. Alright. So if there are any doubts about the calculation of the transformation matrix, you can ask me now. Otherwise, we'll move on to the next one. Alright. So the next one is matrix exponential. Okay, so this is going to be similar of the similar form as the exponential of a scalar, right? So e to the power x, when x is real, we have this, right? 1 plus x squared by 2 factorial and so on. This is actually summation of let's say j equals 1 to infinity. Then we have 1 by j factorial to the power j. Oh, sorry, 0 to infinity. Okay. So in case of a matrix, let's say that A is an n by n matrix. We need to find out what e to the power 80 is. A is a real number. So this is going to be identity of the same size as the A matrix plus E times T plus ET squared by 2 factorial and so on. Alright. So this will appear in the solution of the state space equation. Let's write this down. X plus A. Okay. So this is a homogeneous system because the input is 0 and we need to find out what the solution of this system is. So you can recall from the lecture that given this initial condition, we are denoting it by x sub naught uh, x at any time t is going to be e to the power at. This is again is going to be an n by n matrix. You can see it from here, right? These are just sums of n by n matrices times x at 0. So this can also be written as phi t times x0, but this is known as the state transition matrix or ST. Alright. Also recall that there were many ways to calculate the state transition matrix, and one of them was using the Laplace inverse. So phi t is Laplace inverse of Si minus A inverse. Alright, so as this is clear, let's see a question. So I'm going to write down the A matrix directly as a second order system. And the question is to compute the homogeneous solution or the free response. So let's assume that we have some x naught. So x1 naught and x2 naught. What we need to find is e to the power 8. Okay, so let's see. That is Si minus a. That is going to be s minus 1, 2, and s plus 3. Okay, so this is a 2 by 2 matrix. The inverse is very easy. We have the determinant in the denominator, so s square plus 3s plus 2. Interchange the main diagonal elements and reverse the sign of the off diagonal elements. So this is 1 and minus 2. So you know that we have to take the Laplace inverse of the whole matrix. So for that we have to perform partial fraction expansion. So let's factor this out first. So let's see. S equals minus 1 is, yeah, and what's the other root? I guess it's 2 minus 2 because this is 4 minus x plus 2. Yeah, this is going to be 1 upon s plus 1 s plus 2. So let's see, one of them is just s plus 1 and s plus 2. We can multiply by minus 2 later. So what's C1? Can anyone compute this? Let's see. So C1 is going to be evaluated at s equals minus 1. So first one is 1. Okay. The next one is minus 1. Let's see. Yeah. And then we have the other ones too, right? So this is s upon s plus 2 evaluated at minus 1. And s over s plus 1 evaluated at minus 2. So is this what we got for this case? Just check once. Okay, so We already know the Laplace inverse of each of the individual terms, so let's write that down directly. Laplace inverse of Sm minus A inverse is going to be, first is Laplace inverse of S upon S plus n s plus 2, that is minus of e to the power minus t plus 2 to the power minus 2t plus 3 times e to the power minus t minus e to the power minus 2. Then for the second element, we simply have e to the power minus t minus e to the power minus 2t. For this, we have minus 2 e to the power minus t plus 2 to the power minus 2t, and the last one is simply from here. So you can just simplify the first element. It's going to be e to the power minus t, and then the rest of them remain the same. Okay. So this is phi of t or e to the power t. So x at any given time t is going to be this matrix e to the power 80 times x1 0 and x2 0. So you just have to substitute the time. Alright. So this is alright. Let's see. State transition matrix for a third order system. Okay. So again we have a homogeneous system. So x dot is 0 0 minus 2 0 1 0 1 0 and 3 times x, and we have the initial state. This is 0 1 0. So we need to compute e to the power 80. Okay, we first have to compute SI minus A inverse. So we have S minus 1, S minus 3, 0 2 0 0 1 minus 1 0. Alright, so we can compute the inverse of the matrix. So this is going to be long. So what I'm going to do is this 1 upon the determinant of SI minus A inverse and its conjugate. Alright, I'm going to write this down directly. You can check it later. This is S minus 1 squared and S minus 2. And then we have a 3 by 3 matrix. S minus 1, S minus 3, 0, minus 2, S minus 1. 0 again, S minus 1, 0. So now we need the Laplace inverse of each of the quantities. We have a square here. So let's see how the partial fraction expansion turns out. This is going to be C1 upon S1 S minus 1 squared. Let's see 1, 2. This is for the first root, so it's going to be C11 plus C12. You can use some other notation if you like. And then we have C2 over S minus 2. Alright. So you can find out what these coefficients are. So for example, C2 is going to be 1 over s minus 1 squared evaluated at 2. This is simply 1. Then we have C11. This is going to be 1 over s minus 2 evaluated at s equals 1. This is simply minus 1. So now we have to determine what C12 is. So for that, let's expand the left hand and the right hand side of this equation. Alright, so we have 1 equals C11 plus C12 s minus 1, sorry, s minus 2 again, and then we have we have s minus 2 and C2 s minus 1 square. So why are we doing this? So if we just multiply the left hand and the right hand side by s minus 1, what would we get? 1 over s minus 1, s minus 2. This would be C11 over s minus 1. This is fine. And then at s equals 1, what happens is that these and these terms approach infinity, right? I mean, this whole term, this whole term. So that's why we can no longer adopt this approach. So what we are doing instead is just expanding both the sides. Alright. So we already know what C2 and C11 are. So let's substitute those. Minus S is going to be minus of S minus 2 C12. We have S squared minus 2S minus S plus 2, and then we have 1 times S minus 1 square. Now let's just expand this. And we have minus S plus 2. Okay, so let's club terms together. So S square are C12 plus 1. And we have some S terms minus 1, minus 3 C12, and minus 2. Then we have plus 2, okay, plus 2 C12 plus 1. Right, so let's transfer this here. And I think now we can just compute the like parts of S on both sides. So let's see if we get something. So this one by C12 should be minus 1. This, then we have 2 C12 minus 3 T0 or C12 minus 1 T0. Okay, so we have contradictory statements. Just a second, let me check if there's a mistake somewhere. So C2 and C1 are fine. Okay, this is alright. sorry, okay. This is this. Yes, so this implies C12 is minus, and the same equation from here. So now we know what C12 is. So now we can just do the partial fraction expansion here and we get the results. So I'm going to write down the final results and check that out later. So it will be 2 e to the power t, t 0, and yeah. So we have already been given an initial condition. There is just one in the second row. So x at any time t is going to be 0 e to the power t and 0. I guess we don't really have to compute this Laplace inverse. Yeah, so there is s minus 1 terms everywhere in the denominator. So what we have to do is just compute 1 over s minus 1, s minus 2, for example s minus 3 for this term, and then similarly for the rest of the terms. Alright, so if this is okay, let's move on to the let me just see what's the problem. It's 4. So solution of non-homogeneous state space system or x dot equals ax plus b. So we already know the solution of this, and we need to find the solution due to the presence of input. Okay, so just recall from the lecture that x at any time t, let's say this is some initial condition x naught, and x at any time t is given as, first of all, the homogeneous solution. So e to the power at times x naught plus, this is the particular integral. You start from some t naught. So let's say that this is some general time t naught, not 0, to the current time t, and then we have e to the power a t minus tau. Tau is the dummy variable here. E t tau. And if we have translated the time from 0 to t naught, so this also changes. It is going to be e to the power t minus t. Okay, so in other words, this is going to be 5t minus t naught times x naught plus 5 t minus tau d u tau dt. Alright. And what's the solution of this? So we already know the solution in terms of the Laplace inverse for the homogeneous case. So for this, what we can do instead, this is going to be this Laplace inverse of SR minus A inverse times x naught plus Laplace inverse of phi is b, its constant matrix times u of x. So let's look at some questions now. Okay, so now we have a state space model of second order, so x1 dot and x2 dot. So let's see. Okay, so 0, 1, 0, 1, minus 1, minus 2. So this is the CCF form, right? And we have already been given an input, so it is the step response 1 for t greater than equal to 0. So this is the step response this, right? And it was 0 before times 0. Alright, so we already know the A matrix and the B matrix. So let's first find out the state transition matrix then. Sorry. Okay, so what is this? Si minus A is S minus 0, S plus 3 minus 1 and 2. It's a second order system. So then versus determinant is S square plus 3S plus 2. Interchange these two and reverse their signs. Alright. So we have already seen the factorization of this. It says S plus 1, S plus 2, S plus 3, 1, minus 2 and X. So what's the next step? Partial fraction expansion, right? Okay, so what I'm going to do that is write this down directly. You can check later. We have already done this computation before. This is 2e to the power minus t minus 2t. So then we have e to the power minus t minus 2t. So, okay, so this was fine. The main part of this question is to compute the second term. So let's see. Okay. So we have, it is the initial time is 0. Yeah, 0 to t. So we have e to the power a t minus tau b root of d tau. So from 0 to t, this is just 1. And what's b? B is the vector 0, 1. Let's check. Yeah. So this is simply, so what we can do is e to the power minus t, e to the power minus 2t. Just take the second column. So, and then have to replace these t's by t minus tau. So t minus tau and now just integrate with respect to tau. Okay. So t is constant in this integration. Let's see. So we have e to the power minus t and the integral of e to the power tau. So this is just this minus e to the power minus 2t and we have 1 by 2 e to the power 2 tau. And then the next one is minus e to the power minus t and minus e to the power plus tau plus 2 times e to the power minus t into e to the power tau. So this integral from 0 to t. So I'm just going to write this down directly. Just a second. Alright, let's see. calculate these first. This is simply 1 minus e to the power 1 to the power. Okay, so this is mistake here. So this is not correct. Huh? Let's see. Integrate the first term, so we have e to the power minus t minus tau, e to the power minus t minus tau beta. So this becomes e to the power minus t into the power tau from 0 to t over 2. So we have e to the power t minus 1 minus half, and then we have e to the power 2t minus 1. Similarly, you can compute the integral of the second element, and then we already have e to the power 80 here. So what's xt then? E to the power 80 xt plus the integral of this. So this gets substituted here. So I'm going to write this down. Xt becomes, sorry, this is going to be x0. So this is 2 e to the power minus t So I'm going to write down the state transition matrix right now because we have to multiply by x naught. So to the power minus 2t, it's written above. Minus 2 to the power minus t plus 2 to the power minus 2t times the initial condition. So let's assume that this is some x1 0 and x2 0 plus the particular integral term. So you can check this later. This is half minus e to the power minus t plus half e to the power minus 2t e to the power minus t and e to the power minus 2. Okay. Now if the system starts from 0 initial conditions, so if x naught, which is 0, then the first part is 0 and we just have the forced response. So this is going to be half e to the power minus t plus half e to the power minus 2t e to the power minus 2. So this is the state free response. Alright. So this is fine. Let's see another question. So again, we have a force system. So x dot equals x1 dot x2 dot equals and the initial conditions are given this time. So it says 0 initial conditions. We also have the output y. So it says the first state. So we need to determine what the output is. Okay, so alright. So it's also given that the input again is just the step response, so 1 for t greater than equal to 0. So you already know by now how to compute the state transition matrix e to the power 18. I am going to write that down directly. Okay. This is something like minus 0.5t. Sorry, sine of. So if you have not seen the Laplace inverse, how does it get to cosines and sines? Let me just show you. So I'm going to write this down directly. Si minus A inverse. This is a 2 by 2 matrix, so you know how to compute the inverse. This is S plus 0.5 minus 0.5 over, and then we have minus 0.5 and then we have S plus 0.5 minus 0.5 over. Alright. So now we need to compute the Laplace inverse and get to y, right? So let's see. That means we need to remember this part. So alright. So get S square upon S square plus A. And we have to check from some table. Just one second. Just a second. Sorry about that. These are squares, and when it's S in the numerator, it is cosine of this is fine. We have sine of it. So there are tables in all the control systems theory books. You can refer to them. You can refer to Ogata's appendix or any other ones. So these are the Laplace transforms, and if they are shifted, so let's see by something. Just a second, I have to write the simple expression. Okay. So if it is shifted by some, let's say, some b, So, and then we also have a upon s plus b squared plus a squared. So this shift, this becomes e to the power minus bt, and then cosine of at as before, and then again it's e to the power minus b times t sine of a of t. So by using these properties, you can see that this is the Laplace inverse. So let's check. So this is shift 5.5. This is also shift 5.5. Okay. And to get this in one of these forms, what you can do is multiply and divide by 0.5, and then you have this plus 0.5 squared plus 0.5 squared, and this is nothing but 2 times, so the Laplace inverse of this is 2 times uh, sine of t, but a shifted version. So I think this is what we got. Yeah. So this part, and then you can compute the rest of the terms too. Alright, so what we need to actually find out is the force response. We have, okay, so we have the homogeneous response. Alright, so what's the, okay, so the particular integral or the force response is 0 to t e to the power a tau, and then we have d u tau d tau. So this is 1, and let me just see what b was. 1.5 times u, sorry, 0.5 0. So we can substitute e to the power a tau and compute the integrals element-wise. So if this is clear, I think we can move on to the next part. So if you have any doubts up to this point, you can ask. Alright, so this is clear. Let's move on to the properties of the state transition matrix. Okay, so state transition matrix, or STM sometimes. Okay, so we have this system, and the state transition matrix has the following properties. So this is just recalling the properties from the lecture. So d by dt of phi of t, or phi dot t, is actually a times phi of t. Why? Because this has to satisfy the differential equation, right? So if x of t is phi t at 0, then x dot of t is phi dot t x 0, and we can just substitute here. This implies phi dot of t is a phi of t. The next property is that phi at time 0 is identical. This is also obvious, right? Because x at any time t is phi at any time t times x0, and if you are at time 0, then xt is equals to x0. So phi t has to be the identity matrix. Okay, and then we have the third point. So, so we need some x at, for example, at some time t2. So we are at, for example, 0, t1 and t2. So if we start from 0, then we have this state transition matrix. But we can also begin our solutions from t1, right? We can go up to t1, stop there, and then use these as initial conditions and go to t2. So in that case, x at t2 is going to be phi of t2 minus t1 times x1, or x at t1. And what is x at t1? It is simply phi starting from t0, x t0, or sometimes 0, whatever you are considering. So this implies that phi t2 minus t0 is actually phi t2 minus t1 and phi t0. Okay. So we have two more properties. So phi inverse t is phi minus t. So for example, you start at time 0 and you flow along there and you get to the solution at x at t. Now to get back to the initial condition, what you can do is apply phi of minus t to xt. Okay. And then you have the last property that phi t is a non-singular matrix for all finite t. That is determinant of phi of t is non-zero. Okay, so let's look at some questions now. Okay, so you have a system which has some A matrix, and what we are given is the state transition matrix e to the power A. Okay, so this is given by 1 plus 2t e to the power some scalar at. So A belongs to the real numbers. Then we have minus t e to the power at. This is 4t e to the power at and 1 minus 2t e to the power at. Okay. So the question is, reconstruct the matrix A. So it's given that there is a matrix A and its state transition matrix is e to the power at. So then what are the properties of the state transition matrix? At time 0 it should be identity, right? So it's a very important property. You'll see that here how we can use that to construct A. So e to the power A0 is 1, 0, 0 and 1. So this is identity. So it's a state transition matrix. Now let's see. So is there any property which relates A and e to the power at, or which relates A and phi t? It does. It was the very first property I will say. So phi dot t is A phi of t. So let's see. So d by dt of e to the power at is A times e to the power at. Alright, so let's see. The derivative of e to the power at is A times e to the power at plus 2at e to the power at plus 2 to the power 8. Similarly for the rest of the terms. So minus e to the power at minus 8t e to the power at Then we have 4 e to the power 80 plus 480 to the power 80 is this, and minus 2 to the power 80 minus 280 to the power. And this property holds for all time starting from the initial condition. So let me just write this down. For all t greater than equal to 0. Okay. So it also holds for t equal to 0 then. So let's see. Uh, d by dt e to the power 80 computed at t equals 0 is going to be a times e to the power 80 computed at t equals 0. So this is identity at t equals 0. Then you get what is equal to. So a is let's see, a plus 2, and then I guess this is just minus 1. Sorry, that's right. Then we have 4 and then 8. Sorry, a minus 2. Okay, so you have found the matrix A given the state transition matrix e to the power 8. Alright, now let's look at another question. Okay. So it's given that phi t or e to the power 80 is given by 60 minus okay. So we have to find out what A is. So we have some time. Let's calculate this. So what's the first part of this? Anyone? So how should we begin? Okay, so just check if this holds true or not. Is this true? It is, right? You can just substitute t equals 0 here and you get this. So what's the next step then? You have to compute this. So please compute this and let me know. There are just 4 terms that you have to differentiate, so you can do this quickly. So what's the first term? Minus 4 e to the power minus 40. We have not substituted 0 as of now. What's the next term? This one. So you can unmute yourself if you have the mic. So this is going to be, yeah. And what are the rest of the two terms? I think you can check from it. Just let me know if this is incorrect. Yeah. Okay. So then we just have to apply the property again, right? At t equals 0, this is exactly equal to. Okay, so let's just compute now. This is -4 minus 6 plus 2, and this is a times just the identity, right? So we just have this matrix -4 -4 minus 3 minus 1. If you need to check your solution, what you can do is that you have this a now, and then just check quickly if e to the power 80 is this one or not. So let's just check the first term or something. Xi minus a is going to be x plus 4, x plus 1, 5, 4 and 3. Now we know how to compute the inverse. Sorry, this is not square. Yeah. Okay, so we just have to compute what this is using partial fraction expansion. This is easy. So what are C1 and C2? Can you compute this quickly? -12. Okay, just 1 second. C1 is 1 over s plus 0.5 evaluated at -4. It's not -12, right? Just check if we're getting it correct. Yeah, you're right. Okay, so let me just factorize this quickly then. Okay, uh, s square plus 4.5s plus 2 minus 12. Hmm, okay, so what are the roots then? So this is positive. Okay, so I think we'll need a calculator for this. The purpose of this is to check out if the A that we have computed is indeed the correct one. So we will have to factorize this. Okay, so let's just leave it as an exercise. If you have any doubts, you can post this on the announcements portal. So just check uh, if e to the power 80 uh, computed using this A. This is minus 4 minus 4 minus 4 is the same as given in the question. Alright, so I think we can end here for today. If you have any doubts regarding the assignment, you can ask now. Alright, if there are no doubts, we can end for